Hello, welcome to this lesson of our study of calculus 1. This particularly in limits and continuity. Okay, so if you have not subscribed to the channel, kindly subscribe to support the channel as well. Alright, let's start. So limits and continuity. Now when we say limit, what does it mean? Okay, so this is how the general definition looks like. That the limit of a function f of x as s approaches a is equal to L. I mean, the L here is the limit we are talking about, is what we call the limit. Okay, now this means that when we say something is approaching, it's not actually or necessarily x equals a or s approaches a. Okay, what I mean is that x approaches a is not the same as s equals a. Okay, but in somehow, some way, when we are computing limits, we just plug in our variable, because the idea here is that we are picking values that are really close to a but not equal to a. Okay, so if let's say a equals 1, okay, if a equals 1, then the limit of f of s as s approaches 1 could be picking values and plugging them in f of x as they are getting closer to 1. What would be the value? What would the value be approaching? That is what we call the limit. Okay, so the values around 1 from the left of 1. Okay, that is I will explain the left hand limit and the right hand limit. Okay, from the left of 1, meaning if I draw 1 on the number line, let me bring in another page. Let's say I have the number line like this. Okay, let me draw it straight for you. Let's say I have the number line like this. Okay, and let's say this is 1. Okay, if this is 1, then from the left of 1 we have values that are close to 1. We can get 0.999. Okay, it's very close to 1. Then when you come here, we can get 0.998. okay, going to the left like that. And from the right of 1 you have 1.001. okay, or you can say 1.0001. let me put it that way. You can also get 1.001, okay, or 00. Let me see, with the first one, let's make it like 005. okay, 3 zeros, right? Then 0 again, 5. Okay, so we have to write 3 zeros for this, then we come with 1. Okay, something like this. So they are very close to 1, but they are not 1. So this is the actual value, or this is the a we are talking about here in this case. Okay, so as the values are getting closer to that, from the both left and the right, what will be the value? What will be the estimated value of f of those values? Okay, plug in those values. Now if you remember, I've done a video on functions, so when I say f of something, you understand. Okay, alright, so let's talk about that. Is just about what limit is about. Okay, so let's talk about the existence of limit. When do we say that the limit exists? Now the limit exists if limit of f of s as s approaches a minus, meaning when you go to the slides that I said, when you pick values from this side, these values, and plug in f, let's say f of s is equal to, let's say, x. Now as you find the limit of f of s as s approaches 1, okay, so the limit of f of s as s approaches 1 is the same as the limit of x. F of s is x, okay, as x approaches what? 1. So if this limit should exist, then we should consider the values from the left of 1, plug them in here, and that will give us what? First of all, when you plug in 0.998, we get 0.998. okay, f of s is equals to x. When you plug in 0.99, you get 0.99. okay, then you go to the right of 1, these values, okay, and plug them in. The first one will give us, or from the far end, will give us, first one will give us 1.00001. the next one will give us 1.00005. Now you could see that all these values, when we round them up to one decimal place, they are, all of them will be equal to 1. okay, we'll run all of these up, so approximately they are all getting to 1. So it means that the limit exists. Since when we move from the left, we're approaching 1, and from the right we're also approaching 1, and That is why we say the limit, or when we say that the limit exists. It only exists when the left-handed limit, okay, that is limit of f of s as s approaches a minus equals limit of f of s as s approaches a plus, and they are the same. Okay, they are equal to a real number. They exist. Okay, that is what we call the existence of limits. Okay, now let's go ahead and pick an example. This is an example. Given f of s to be this is an example of a piecewise function. Okay, so given f of s equals 1 minus x, okay, for the first one, this is a condition within the range of this, and 2s squared minus 2 within the range of that. Okay, so I hope you can see it. Now you're supposed to find the limits of f of s as s approaches 2 minus, meaning values less than 2 but really close to 2, something like 2 point, or sorry, 1.999999, okay, 1.999998. So such values are what we want to plug in and check if, or and ask ourselves what kind of values are we going to get, okay, for the x approaches 2 minus, and limit as s approaches 2 plus, what values are we going to get? And plug in values that are like greater than 2 but then really close to 2, 2.0000015, 2.0000012, 2.0000011, okay, something like that. Or in effect, since we have range like this for the first one, you could see that it said limit of f of s as s approaches 2 minus. So values ranges, or range of values that are less than 2 and then really close to 2. With that range, the function is given as this. Okay, 1 less than s less than 2, meaning values between 1 and 2. Okay, so you can get those values that are really close to 2 but then less than 2 inside that range, and with that the function is given as this. Okay, so you can also plug in just 2 straight away using that range when you have a piecewise function like this. Then you go to values that are greater than 2, okay, but close to 2. With that one too, we have this, because this is the range given. The range is from 2 to, values that are within 2 and 3, okay, but then really close to 2. You see that 2 less than s less than or equal to 3, although 3 is part of that range, but then the values that are really greater than 2 but close to 2 are also in that range. Okay, so we will use that function there. Okay, we'll use this function for the second one, this one for the first one. Okay, so let's start solving the question and see. Okay, so for 2 minus, for the first part, that is a, f of x was given as what? In the values that are really less than 2 but then close to 2, the f of s function was given as x plus 2 in the range 1 less than x less than 2. This is what we'll use for the 2 minus. That's the range. Okay, so the function given there is minus s plus 2. So the limits as s approaches 2 minus of f of x is the same as the limit of minus x plus 2 as s approaches what? 2 minus. And when you plug in, you take your time and plug in all these values, you see that the values will be approaching 0, or in other words, let's put in 2 and see. When you put in 2, you get minus 2 plus 2, which will be 0, and you put in 1.999999, which is very close to 2, and put it here, you see that those values will be approaching what? 0. Okay, so that is the solution to this. Now we go to the b part. Now for the 2 plus, the range within which we have 2 plus is this range, 2 less than x less than or equal to 3. Okay, so 2 less than x less than or equal to 3. With that range, the function given there was what was the function? 2x minus 4. So limits of f of x as x approaches 2 plus, okay, we got the limits of 2x minus 4 as s approaches 2 plus, or you can say 2 because since we know the range, okay, and this one too will be approaching 0. You could see that when you pick values, like let's say if I pick 2, I consider, first of all, sometimes consider the value itself. If it doesn't exist at that point, then you check close values. Okay, so neighborhood values, like which will be greater than 2, will be 2.000001. When you plug them here, you see that the values will be approaching 0. Okay, so the next question was, you're supposed to find these two. Fine, we are done with them. The next one is, does the limit exist? And if you could see in our first slide, we said that the limit exists if both the left hand limit, which is the minus aspect, and the right hand limit, which is the plus aspect, are all existing and they are the same. Okay, so this is the left hand limit and this is the right hand limit. Okay, so does the limit exist? Yes, it exists, since both limits are equal. Okay, so the C part, you just said it exists. Yes. So does it exist? Yes, since limit of f of x as s approaches 2 minus is the same as limit of f of x as s approaches 2 plus, and they are equal to 0. Okay, they exist and they are equal to 0. That is what we just mean by does the limit exist. Okay, so let's move ahead and go to what we call the continuity. Okay, so let f of s be a real function and a be a point in the domain of f of s. Then f of x is continuous at a if the limit, okay, so you can see that there's a condition here, if this condition is satisfied. Okay, if this condition is satisfied, if the limit of f of x as s approaches a, okay, so the function f is continuous at that point if the limit of f of s as s approaches that point is equal to f of a. That means the function evaluated at the point is the same as the limit as s approaches the same point. Then we say that the function is continuous at that point. Okay, this is what I mean. Anything apart from this is discontinuity. Okay, so if this condition is not satisfied, then we have discontinuity. Alright, so let's pick an example. Show that f of s is continuous everywhere. Okay, f of s is this. F of s is this when x is not equal to 0, and is this when it's equal to 0 when s is equal to 0 when s is equal to 0. Okay, so with this you can even evaluate f of s. The first one, f of s equals s squared over x is the same as x. Okay, we can continue and evaluate this. So the question is, for this to be continuous, the limits at any point, we are supposed to show that everywhere at any point the function is continuous. So let's first of all consider at x equals 0. What will be the limit as s approaches 0 of f of s, which is x? It will be equal to 0. And what is f of 0? Is also equal to 0. That one was even given here. So since the limits, because the reason why I didn't do the left hand limit and the right hand limit is because whatever way you do, you get 0. Okay, you can try from the right of 0 and the left of 0 and see if they are the same. And when they are the same, then it means the limit exists and it's equal to 0. Okay, f of 0 is 0, and then the limit as s approaches 0 is also 0. So this means that it is continuous at 0. So you can try at equal to 1, at x equals 2, and at s equals, let's say, 10, and see. And you really come to a conclusion that this function is actually continuous at everywhere. Okay, so at x equals 1, the limit as s approaches 1 of x is just 1, and the limit, and f of 1 is also 1. So it means since the limit is equal to the function evaluated at that point, means that the function is continuous at 1. Okay, you continue with the 2 and 10, and you see that it's indeed continuous. So continuity is just simply like that. When the limit exists and is the same as the function evaluated at the point, then that is why we see it is the function is continuous at that point. Okay, discontinuity. So when the condition for continuity is not attained, that is, if this is not attained. Okay, that is what I just said. So it means that for this to be discontinuous, or for a function to be discontinuous at a point A, then it means either the limit does not exist, or the limit exists but not equal to f of a, or either f of a does not exist, Okay, such things like any condition that will disprove this or anything that will disprove this condition, okay, it makes it discontinuous. But we have types of discontinuity. You have removable discontinuity and you have non-removable discontinuity. So let's talk about the removable one. Okay, so with the removable discontinuity, sorry, this one is supposed to be discontinuity. This with the removable discontinuity, this occurs when limit of f of x exists. Okay, the limit actually exists, and either it is not equal to f of a, or f of a is not defined at the point a. Okay, so this is very simple. For the removable discontinuity, the limit exists, but either f of a does not exist at that point, or f of a is not equal to the limit at that point. Okay, so you can remove this discontinuity by redefining the function at the point a. So you have to redefine it. Alright, let's take an example and then let's go through it, and I believe after the example you understand. Okay, so show that the function f of s equals this, okay, has a removable discontinuity at s equals 3. So first of all, what do we mean by removable discontinuity? Okay, we said that the limit actually exists at the point, but but the function evaluated at that point does not exist, or the limit exists and it's not equal to the function evaluated at that point. That's why you call the removable discontinuity. Okay, so let's first of all find the limit and see if the limit exists. So limit as s approaches 3 of s squared minus 9 s squared minus 9 over 3x minus 9. This is the same as, for limit you can be evaluating it. This is the same as limit as s approaches 3 of x plus 3 x minus 3, difference of 2 squared, right? 3 into x minus 3, and this can take this off. So when I plug in 3, this will work. So we'll get 6 over 3, which is equal to 2. The limit exists. So it means that we have to check about the function evaluated at 3. So f of 3 will now be equal to 3 squared, which is 9, minus 9, which is 0, over 3 times 3, which is also 9 minus 9. This is equal to 0 over 0, and this is undefined. Okay, this is undefined. So, and undefined means that it does not exist. Okay, the limit does not exist. Okay, sorry, it's not a limit actually, it's the function evaluated at the point 3. Okay, I'm really sorry for that. So f of 3 does not actually exist. Okay, so what we can do is, let's try to remove it at the point x equals 3 and see if indeed this will work. Okay, so given the function as f of x equals s squared minus 9 over 3x minus 9. First of all, what you have to do is, well, just ask to show that it has removable discontinuity at s equals 3. So once the conditions for removable discontinuity, that is when the limit exists, but then the f of a, that is this time f of 3, does not exist or is not equal to the limit, then you have removable discontinuity at that point. We've already shown that, but we want to remove that discontinuity. Okay, now redefining it at the point s equals 3, we have to factor s equals, we have at the point, let me show you here, at the point s equals 3. Okay, when I take 3 to the other side, I have x minus 3 equals 0. So I have to make sure that I get this factor x minus 3. Okay, that is how you remove it. At the point s equals 3, you have to, put everything to the left side and get s minus something equals 0. This time you are dealing with 3, so s minus 3 equals 0. And make sure that this factor appears in both the numerator and denominator, or appears in your function, and do something to it. Okay, so to make sure that this happens, you have to expand the top, sorry, difference of 2 squares. Okay, and x minus 3 over 3 into x minus 3. You see that s minus 3 has happened or has appeared on both the numerator and the denominator. Okay, so this can take this out. Alright, then we have f of x now being equal to 1 over 3 x plus 3. Now you can check this and find out the limit as s approaches 3 of this function, and find s, or simply simplified f of 3 of the same function f of x, this function. You can see that they will be the same, so we have removed the discontinuity in this function by just redefining our function about the point s equals 3. I hope this is okay. Alright, let's go to the next one. That's a non-removable discontinuity. This one, you can't do anything about the discontinuity. It's just discontinuous. You can't remove the discontinuity. You can't do anything to it, and all you have to do is just say that it's discontinuous. Okay, and you have it is in two parts. So this, first of all, when at the point x equals a, the limits, that is the left hand side or the left hand limit and right hand limit exist but not equal. When they both exist, the limit actually, this in this way, you just say that the limit does not exist. Okay, that's what you should know. When you go to the previous one, we said that the limit, what, the removable and the limit exists, but then it's not equal to f of a. But with the non-removable one, the limit does not exist. That is the first thing you should know. But what makes it non-existent, or what causes its non-existence? It is when the limits from both sides are not the same. When they are not the same, they exist, but they are not the same. We call it jump discontinuity. They both exist. Okay, just know this side. The limit exists, but not equal. That is the left hand side limit and the right hand side limit exist, but they are not the same. That's why we call it jump discontinuity. But, or we have the other way, either one of them is either plus infinity or minus infinity. Okay, that is also another form of non-removable discontinuity. Okay, so is either they don't exist. Okay, the limit does not exist. I mean, either the left hand side limit does not exist or the right hand side limit does not exist, or they both exist but not equal. When they both exist and they are not equal, we call it jump discontinuity, and that is also part of non-removable discontinuity. Okay, so with the non-removable discontinuities, particularly about the limit which does not exist. Okay, so let's move on to an example which will show us jump discontinuity in this. Okay, non-removable discontinuity. Show that f of x has a jump discontinuity at s equals 1, and this is our f of x. Okay, is equals with that. With the first range, we don't have any problem with that because it doesn't have a range for 1. Now with the second range, we have a problem because with the second range, that is where you have values less than or equal to 1. Okay, so the left hand side limit of 1 is there, and then with the third range, this one, the right side of the limit is also there, because the right values that are at right of 1, meaning values that are greater than 1 but really close to 1, are also found there in the third range. Okay, so we are going to use the second and third functions. Okay, so with this one, let's start quickly. Now we have to first, we are saying that we are doing everything about what 1 s equals 1. So remember, this is a non-removable discontinuity, and then secondly, it is a jump discontinuity because we are saying that both the left side limit and the right side limit exist but not the same. Okay, so first of all, we have to find the left side limit of 1. So the limit of f of x as s approaches 1 minus, okay, is the same as limit of, now 1 minus, what are the values that are really close to 1 but less than 1? Okay, it's this range, the second range. Okay, so you have to write that function down. So limits as s approaches 1 minus, okay, or 1, since we know the range is actually for 1 minus, so 1, then what is the function? The function there is what? 2s squared is 2. So when you have the range, you can just write approaches 1 and go. But the range is there. The range shows that the range in this function has given that at that point, at this function, okay, the values that will satisfy this equation will be less than 1, but really close to 1. That was the function's range, okay? And this will be equal to what? 0. Okay, so let's find the limits of f of x as s approaches 1 plus, and that is the same as limit of what? Negative x plus 2. That's the range given there as s approaches 1, and this is equal to what? 1. Now you can see that they are not equal, but they both exist. Okay, so since limits of f of x, okay, limit of f of x as s approaches 1 minus is not equal to limit of f of x as s approaches 1 plus. The function f of s has a jump discontinuity. They both exist though, okay. For jump discontinuity, they should exist, but they shouldn't be equal. Okay, f of s has a jump discontinuity at the point where x equals what? 1. Okay, so that is the whole idea about continuity and limits. Okay, so thank you, and don't forget to subscribe to my channel. In our next video, we'll talk about asymptote, the horizontal asymptote and vertical asymptote.